I do know that I'm going to be gone on the 27th, so I know next week we'll be here on Monday, probably gone the next, we'll be gone the next 2 days, and I don't know if I'm going to be gone the 29th or 30th. But I'm sure you guys probably don't mind if someone's gone right before the 4th of July weekend, right? As far as that goes. Now, any questions from before? By the way, I don't know if that says for official use only, but the Navy gave me that. It's okay, classified. Unclassified. Okay. Does it say for official use only though? No, government use only. Down at the bottom, it's stamped government use only. However, it was given to me by the government. So anyway.
So do we ever tamper with? Do we ever consider making a titanium hull?
Yeah, but the reasons that we haven't. First, you all know the Alpha Sub was tremendously noisy, but the Naval Research Lab had determined that titanium has this property called a creep fatigue interaction. So if it's under a high sustained stress and it gets a slight cyclical stress on top of it, it just propagates fatigue cracks at a tremendous rate. And so the Naval Research Lab had discovered that, and that was one of the things that people, before you design and build one of these things, as expensive as it's going to be, aside from the fact that even if you were talking in 1980 dollars of $30 a pound for the material, if you use my rule of 10 multiplier for the cost of the structure, you're talking $300 a pound fabricated for something that weighs quite a bit. And you start figuring the hull cost, you're talking a $1 billion hull in 1980. Would you rather have 5 or 10 steel submarines versus 1 titanium submarine? Well, that was kind of the trade-off. Aside from the fact that technically there was this creep fatigue interaction, and the little things I've heard, there are a couple of things I know about. The only time I've ever used the security clearance was to see some foreign technology in titanium. Okay, and that's as far as I can go talking about that, although it's been 25 years now, so who knows. And I know a lot of this stuff has come out since. Okay, so I can talk about some of these things now, and some of the things are not classified. I haven't told you anything that I learned in 1980 or 81 that's classified, but the creep fatigue interaction, we think the Soviets ran into that problem. They either didn't know about it or they ignored it, okay? But then they had problems, the Alpha Subs, and I've learned a lot of this from people, people in your classes before you. The Alpha Subs were so lightweight that they didn't really have adequate shielding between the nuclear compartments and the other compartments. They had some leakage problems, we think. So they were noisy, and even though they could dive deeper than the collapse depth of our depth charges, this one guy I know out in Colorado says, well, it depends on the type of depth charge, okay? If you hit them with the right depth charge, you only have to be within a few miles, right? Well, yeah, if you start using those types of depth charges, you really got serious problems, okay? But they would go faster than our destroyers could go on the surface. They would dive deeper than the collapse depth of our torpedoes, although I'm sure I don't know if it's collapse depth, but we had problems. We didn't have anything in the design at the time other than going to big weapons that we didn't want to use to actually track them or follow them or anything. So it was a huge concern, but quickly, as we found that they were having more problems and they were so noisy, you didn't have to get very close to them to follow them, okay? They were just tremendously noisy. But then they had cracking problems, we believe, from this creep fatigue problem. We know they had cracking problems because the cracks were some of the things making the noises. I mean, they had whole stiffening webs that were probably rubbing against each other and things like that because they were cracked all the way through. So, yeah, it's a wonderful material, and we want to build the next Alvin, deep diving submersible out of titanium, but it's still very expensive per pound. When they couldn't find anyone to fabricate, any industrial people to fabricate the first Alvin hull, Mare Island Shipyard did it because no industrial company would take it. And then the U.S. Navy, the people at David Taylor Annapolis, had spent most of their time working on gas metal arc welding of titanium, which is what Dan Reese had done his master's thesis when he was a student here in 1983, because it was a hot topic. Well, it turns out I met with Gurevich in 1980. Jimmy Carter had detente with the Soviets, and there was this big electrometallurgy exchange, and Professor Grant from MIT, who's since passed away, but he had left the Soviet Union when he was 5 years old, so he spoke Russian. He was head of this huge delegation, 37 scientists in the late 1970s went over to the Soviet Union as part of this electrometallurgy exchange. And the Baton Institute was the exchange institute. I was a young assistant professor, and I didn't get to go in that first one. It was all big wigs, you know, department heads around the country in material science and stuff. And the next time they ever went over there, there were only 10 people that went. And the next time, there were only 2 people that went, Professor Kelly and myself. So Kelly had a research contract out of the National Science Foundation. Ronald Reagan was closing everything down, all this exchange with the Soviets. But I got to go, and the Soviets were trying to keep the exchange open. So they were showing us everything and telling us all kinds of things in order to be cooperative. And Sekeli had left Hungary in 1956 with a weapon as he got to the Austrian border and walked across, you know, in 56. He went to Imperial College and eventually became a faculty member here. He had a research contract. He didn't want to go to the Soviet Union alone. I was still a young assistant or associate professor, and I wanted to go see the Baton Institute before they closed it, before Reagan closed it down. So we went over there together, and he spoke a little Russian because growing as a kid in Hungary, he had to learn Russian in schools. But I sat down with Gurevich for 2 hours with a KGB agent sitting right next to Gurevich, across the table. Gurevich was a wonderful man. He told me everything. He's a pure scientist. You know, I don't think he had any political leanings. The KGB agent was not stopping, you know, any of the conversation. And I learned that they don't use gas metal. And when I tried to describe gas metal arc welding, he kept on saying, you know, it was like he didn't quite understand. And finally he says, oh, no, doesn't work. Okay? And that's what the U.S. Navy had been trying to develop for years. It's what they still claim they have working, okay? Because once you spend all that money developing something, you can't go tell the higher-ups that it doesn't work. It's sort of like HY-130, okay? They spent $50 million developing HY-130, and it doesn't work. But you're not going to go tell people that, right? Okay, I remember sitting down with the chief engineer of the Navy once. The guys at David Taylor said, come over, let's talk to the chief engineer and tell him that HY-130 doesn't work. Okay, and the people who developed it 20 years before had made a mistake, and you'll never build a hull out of it. This is when they were trying to build the SS-721. And we went over and I told him, I said, you'll never build a hull out of HY-130, a full-size hull. I mean, you might build little components, and the Navy has, but it's so difficult to work with. And so titanium's sort of in the same ballpark. Now they're going to make stainless steel submarines, right? Maybe, if we can afford those. Well, it'll be like this. SN-2021. Were they built 2? Or 3? Okay. Any other questions? I don't mind progressions. Okay, joining costs we talked about are equal to, often equal to or exceed the cost of the material. This is just a review of yesterday. The inherent strength of chemical bonds is very high, and I didn't really give you the demonstration I usually give. The bond strength of primary bonds is 1 to 3 electron volts. And 1 to 3 electron volts, in that little calculation I handed out, translates to 1 million to 3 million psi strength. But we know things don't have that kind of strength. Typically, our strongest steels may have 1/10 that strength. And does any of you former material scientists know why that's so? Why metals deform at much lower strength than the theoretical? I talked about defects, and that's part of it, but the defects we're talking about are actually called dislocations in the crystal. How many people have heard of dislocations before in crystals? So many of you have, and even if you're a mechanical engineer, they often tell you it's the mechanical engineers who discovered them in the 1930s before anyone had ever seen them. But the way I illustrate a dislocation, actually the best part of the story on dislocations is the way that Professor Orawan, Egon Orawan was a professor in Hungary. He later came to MIT, and when I came here as a student, he was retired and he was over in mechanical engineering. But Egon Orwan, well, had this nice office at this old palace or something in Hungary, and they had a nice oriental rug or something on the floor, a great big rug, and it was misplaced by 6 inches, and the cleaning lady was in the room, was about to, she said, oh, it needs to be moved. He says, I'll help you, because it's a very heavy rug. She says, oh no, I don't need any help. And all she did is she, taking one of these things, Orwan was trying to figure out why metals deform so easily. Now, people have done those types of calculations. She just put a little wrinkle in the thing, and she kicked it across the room. Okay, she just put a little fold like that in the rug, and with her foot, she just kicked it across. And the thing moved by about 6 inches, depending on how big that fold is. Okay, and she introduced a dislocation. Orwan started thinking about it, and he realized crystals could do the same thing. You could take a broken row of atoms, if you will, in the crystal, and you could sweep it through the crystal, so the force times the distance for that broken row of atoms was huge, because you're going, in terms of atomic distances, you're going 10 to the 10th atomic distances, it takes a very little force. But the macroscopic crystal moves a very small distance with the equivalent, what would have taken a huge force over a small distance, you can do as a small force over a huge distance. And one way to illustrate that is to rip a telephone book into, this is an MIT telephone directory. I have done this with Yellow Pages back in my youth. One of the problems though, and I may not be able to do this, in my youth they used to use cheap paper, okay? Nowadays the paper is reinforced with polymers. So anyway, you introduce a dislocation by just folding the thing, introducing that same type of little bend, and then you grab it with your thumbs and you tighten it, and you can see that I'm only going to stretch the top one, right? All the others are not stressed. So if I do it properly, and the polymers are not too strong, rip the telephone book into it. Okay? By introducing a dislocation. Well, that's why metals don't have the inherent strength of the bonds, because dislocations, mobile dislocations in metals, sweep through the crystal and break one page at a time, or one row of bonds at a time, rather than a whole plane of bonds at a time. Ordinarily, you'd have to break a whole plane of bonds. A whole plane of bonds per square centimeter is about 10 to the 15th atoms. But a whole line is only about 10 to the 8th atoms. It's a lot easier to break, to move 10 to the 8th atoms than to break 10 to the 15th all at one time. So that's why, but if you, in terms of atom-atom bonds, the atom-atom bonds are extremely strong. It's the dislocations that weaken things. Surface roughness and surface contamination are the two factors limiting the bonding of the two materials. And we'll get to these other things as we go on today. Okay. So one of the things that, if we want to start talking about why things, if you bring two atoms together, why they don't bond, it's because of surface roughness, surface contamination. They have inherently extremely high bond strength. And even if you get a fairly poor weld or solder joint or adhesive bond, potentially it can have very, very high strength, even though it's imperfect. Now, in order to get rid of this surface contamination, we can go back to, this is MIT, we're going to go back to first principles, right? And the first principles, if I want to break some sort of chemical bond, if I have some atoms on a surface, and this might be what a crystal looks like, and this would have other atoms to it, okay? These broken lines represent the chemical bonds. Here on the surface, I have unsatisfied bonds. I have bonds that don't have something to share their electrons with. So I'll put those in yellow. And this is what's going to cause surface energy. Those we call unsatisfied bonds. These white bonds are sharing electrons or ionic bonds or metallic bonds, whatever they are, they're satisfied. They form the stable octet rule if you learned in high school chemistry, okay? So they've got their full shells of electrons because they're sharing them, or they've transferred the electrons and they're electrically charged or whatever. But on the surface, these atoms don't have their most stable state of a stable set of octet of electrons, okay? And therefore, they're in a higher energy state. Therefore, surface tension, which is caused by these unsatisfied bonds, surface tension is always a positive quantity. It's always a higher energy state than the lowest energy state of these things forming a condensed phase. I won't form a condensed phase unless the bonds between the atoms are more stable than not being bonded. If the unbonded state is more stable, I'll have a gas. Okay? And they won't be connected to each other. So the very fact I'm talking about a solid or a liquid means these white bonds have to be more stable than the yellow bonds. The yellow bonds in a higher energy state create what we call surface tension. And that little calculation I gave you about 2 million psi for iron basically is using surface energy as a measure of the unsatisfied bond strength on the surface. Okay? Now, if I want to understand how I can use that surface to form a weld or an adhesive joint or whatever, I can go back to those of you that, very few of you probably have had chemical thermodynamics. Most of you are mechanical engineers, and so or physicists, and you've studied heat engines, and steam cycles and things like that. That's what I call mechanical thermodynamics, or mechanical engineering thermodynamics. But if you're a chemical engineer, or a chemist, or a material scientist, you'll study chemical thermodynamics, where we have a Gibbs free energy. You had a Gibbs free energy when you studied thermodynamics before, but the Gibbs free energy in chemical thermodynamics is a function of temperature, pressure, and mu, which we call the chemical potential. And mu sub I, because it's mu of iron or mu of aluminum. It's mu of some species, some chemical species, some one of those, 91 naturally occurring elements. You know I said 91 naturally occurring elements, just for trivia? Everyone talks about 92 naturally occurring elements because uranium is element 92. Because technetium does not exist on Earth. If you look on the periodic table, there's an element called technetium down there near iron and molybdenum and stuff. And it does exist, and we've seen its spectra in supernova where the heavy elements are formed, but it has a half-life of like 10 years. So it never made it to Earth. However, we use technetium in hospitals because we artificially make it. Okay? And because, I don't know, I'm not a nuclear engineer, but I suspect that we use it because with a short half-life, it gives off lots of decays, and it's useful for medical reasons. So we can produce it in a nuclear reactor, but it's never been found naturally on Earth. So of the 92 naturally occurring elements, only 91 exist on Earth. Piece of trivia, next time you're at a cocktail party, you need some more room, you start talking about it, everybody clear out. Okay. So we can use, in order to clean that surface, that contaminated surface, and this contaminated surface wants to pick up all types of junk. It could pick up a carbon dioxide molecule, would come to that surface, or a water molecule, or oil, which I'm not going to write the formula for. In fact, oils and greases are what we put down as lubricants on nice clean surfaces to contaminate them, to give them very low surface energy so they won't bond to each other. Something with a high surface energy, I have these bonds that want to find something to bond to. The higher the surface energy, the cleaner the surface, the easier it is to weld. The more I can dirty it up, the harder it is to form welds, and the better the lubrication is. But I can use any one of these independent variables to try to make welds. I can use pressure, which is one of my 3 independent variables in the Gibbs free energy. And at 1 psi, it's just sort of fixturing, that's kind of holding things together so they don't fall apart, right? At 100 psi, I might have adhesive bonding where I might you know, if I'm putting some Scotch tape on something, I might rub it with my finger, you know, put 5 or 10 psi to get it to bond better. Okay, if you ever had a piece of Scotch tape come off the wall, what do? We'll talk about why this is so, but you just push it on there harder, right? Hoping it'll stick better. We'll get to that later in the course, like tomorrow maybe, or the day after. We have flash upset welding, where you kind of take two materials and you heat them up and you smash them together, and that might be a 1,000 or a couple thousand psi. Cold welding, where we get in tens of thousands of psi. Cold welding, and I'll pass this one around. Yesterday I talked about it. This is a bearing material that has aluminum-clad steel. And they take a big roll of aluminum, big roll of steel, they clean the surfaces, and they run them into a great big roller with tremendous force, and just squeeze them together and roll them out. Okay? Then we have explosive welding, and I don't really have a good example of explosive weld. This is what's supposed to be an explosive weld made by Ford. This one's actually not welded. It's 2 pieces of aluminum, but we learned in World War II, people found, after an explosion, they found pieces of plate that had welded together in the explosion. They were not welded in the very beginning, and the force of an explosion, if you have the right angle, and depending on the material and its strength and whatnot, the angle might be a 10 or 15 degree angle. If 2 pieces of material hit each other with explosive force at a 10 or 15 degree angle and slam together, they will actually clean the surface. There's a surface cleaning, scrubbing action at that interface, that apex of that angle. And you clean the surface and you will form an explosive weld.
Yep. On frigates, the superstructure is aluminum and the hull is steel.
Right.
Where you join the two is a
Explosive weld.
metallic strip that they explosively weld.
Right, in fact, that was going to be my next example. The only large scale, and it's not very large scale, example of explosive welding is the Navy uses it to make, what do they call these joints?
It's just a bimetallic strip.
It's a bimetallic strip. They have there's a trade name for the joint, anyway, of the people who make. There's only 2 people who do this. DuPont used to do it in a valley in Pennsylvania, okay, somewhere in the mountains of Pennsylvania, because, you know, when you're setting off explosives, not all the neighbors like it, okay, so you have to be. And there's a company called Explosive Fabricators just north of, or just kind of west of Boulder, but north of Golden, Colorado. If you come out of Golden, Colorado going north, you'll pass this little canyon, and there'll be a sign to Explosive Fabricators, okay? And so there's only 2 companies that do this, and one of the applications is for the Navy for putting the aluminum superstructure to the steel hull, and they make what they call transition joints. Well, DuPont's name used to be Delta Clad, okay? I don't know where they came up with that, but basically they're making clad metal joints. Some of the chemical process industry folks use it too. If I want to put tantalum on steel to make a pressure vessel, well, tantalum costs about $100 a pound or something like that. It's fairly expensive metal, but it's the only thing other than graphite that will take concentrated sulfuric acid. And there's a number of chemical plant reactions where you need concentrated sulfuric acid. All the gasoline we make uses concentrated sulfuric acid as part of the process, because when you crack your hydrocarbons, you form some moisture, but the moisture poisons the reaction to keep the cracking process going. You have to extract the moisture. Sulfuric acid is very good at extracting moisture. Sulfuric acid has a tremendous affinity for moisture. In fact, it's the best way to clean out your drains, okay, at home. You know, none of you have teenage daughters yet with long hair. I have teenage sons with long hair right now. But actually, I only have one son left at home. But the real problem used to be the 3rd floor of our house where my daughters had their bedrooms. Now, my son's on the 2nd floor. And anyways, you get hair in the drain and it clogs up the drain. You can go in there with roto-rooters every now and then, and you can try to put Drano in there. Drano's worthless, okay? It's basically caustic soda with some aluminum in it. It starts bubbling, makes some gas, and it might be okay for trying to blow out some toilet paper that might get clogged in there, but it doesn't do anything to hair. But sulfuric acid dehydrolyzes most organic materials. If you have a cotton shirt and you get a spot of sulfuric acid on it, you have a nice hole burn right in your shirt. If you get a little sulfuric acid on your hand, it'll cause a burn because it dehydrolyzes your skin. One of the examples I used to do when I was teaching chemical thermodynamics, take about an inch of sugar. You need to do this in a chemical hood. You take about an inch of regular old table sugar, put it in a beaker about this tall, so about an inch of this, and then you put concentrated sulfuric acid on top of it, about an inch. And you first see the sulfuric acid start to turn brown, and then you start seeing a little bubbling, and then you start seeing this mass of graphite or carbon grow out of this, and bubbling, and giving off sulfur dioxide fumes, and sulfur trioxide fumes. So that's why you have to put it in the hood. And this thing will grow because carbon has such low density. It'll grow to fill this thing. It'll grow like 5 or 10 times in volume. And all you've done is you've taken the formula for sucrose is C12H22O11. So if I take out 11 water molecules by the sulfuric acid has such a strong affinity for water, it will dehydrolyze and leave you carbon from the sugar. Okay? One of the most tragic accidents I ever had to work on a few years ago was a guy was working in a chemical plant where they make gasoline, and he fell into a sea of flaming sulfuric acid when a tank blew up. All they found were the steel inserts from his boots because he was dissolved. Okay, he probably wasn't even alive by the time he hit the bath, but nonetheless, he certainly wasn't alive much longer after that. The sulfuric acid has the ability to remove moisture. Why did I get into that? How did I get into sulfuric acid removing moisture?
Explosive bonding?
Explosive bonding, yeah, I was talking about explosive bonding. That's what I was doing.
It was a pressure vessel, like a vessel that could
Oh.
hold the sulfuric acid.
Tantalum is one of the few materials that will hold the sulfuric acid without just corroding away. They actually, sort of like the other material they use is carbon steel, and that's why they had this accident in this plant. The carbon steel lasts about 5 or 10 years. It's just like you use carbon steel for piping on Navy ships, and you know it'll last for 10 years. And you just expect to have to replace it in seawater because it'll corrode. Well, carbon steel goes a little bit faster than sulfuric acid, but they're just supposed to replace it. The problem at this chemical plant is the storage tank for the sulfuric acid, which had hydrocarbons in it because it had been making gasoline. It was dripping. It was, and they had this guy welding on this tank that had, had holes in it. And as the sulfuric acid reacts with the steel, it generates hydrogen. Okay, so you're welding on a tank that's got holes in it, air's getting in to mix with the hydrogen and the hydrocarbon vapors, and then you're going to weld on it. Okay, and they gave a hot work permit to do this job. That's why Saudi Aramco paid a lot of money to this widow. Anyway. So explosive welding, they'll use to make tantalum-clad steel for pressure vessels because the tantalum's too expensive. You make the pressure vessel out of steel, but you line the inside with tantalum for the corrosion resistance. It's an expensive process. The Navy only needs to use a little bit, okay, so far as that goes, in making their steel into aluminum transition joints. But that's how they do it. Near perfect bond, and that piece I was saying around for Ford, there actually is that kind of, they've already machined the critical angle. In that case, it's not explosive bonding. They're trying to use an electromagnetic pulse. So you give a 10 microsecond pulse of electromagnetic energy, and the eddy currents in the material resist the currents you're putting on, and by Lenz's law, you end up slamming the two things together. And if you do it with the right parameters, you basically tear apart your machine, but you also make a weld. Okay. The reason it hasn't been used for welding in the past is because it's pretty hard on the equipment. But you'll generate pressures in 400,000 to a million psi range. Okay. With those type of slamming together pressures, you don't need anything else to clean the surfaces. Okay, if they're coming in at the right angle. Now you can also use temperature. Well, we do cold welding, but cold welding we're using pressure. Okay, lots of pressure, but not so much temperature. Sometimes we add a little bit. We do warm pressure bonding, okay, We do soldering, brazing. We can actually melt things with electric arcs. The actual temperatures are in the 3,000 Kelvin range. People will tell you the arc is at 10,000. That's true, but the actual metal is probably only about 3,000. The boiling point of steel is 3,000. Actually, it's about 3,200 Kelvin, but it's almost 3,000 C. Okay, or a little over 3,000 C. And laser and electron beam have even higher temperatures. Now, some people will say, "Oh, well." In fact, I remember when I was a student and took a course here briefly. In fact, the reason I quit taking the course was because one of the students, the professor said, the temperature of an electron beam is 100 million degrees. And one of the students was naive enough to say, "Professor, what does that mean, 100 million degrees?" And the professor says, "I don't know." And I thought, well, if he doesn't know, I know, so why am I taking this course? Okay. There is an equivalence between energy in electron volts and Boltzmann's constant times temperature. Okay, if I take a voltage and I multiply by the Coulomb charge, E, that's an energy in electron volts. If I take temperature in Kelvin and I multiply by Boltzmann's constant, everybody knows Boltzmann's constant? Boltzmann's constant is the gas constant R, PV is equal to nRT, divided by Avogadro's number. Okay? So the gas constant R per mole and Boltzmann constant are the same, except Boltzmann's constant is the gas constant per atom, or per molecule. So Boltzmann's constant is just the gas constant, PV is equal to nRT, on a per atom basis. And we know bond energies are on the order of 1 to 3 electron volts, and KT, Boltzmann's constant times temperature, I can figure out an equivalent temperature, or actually I can figure out an equivalent voltage for a given temperature by just dividing the KT energy by the electron, the Coulombic charge of the electron. I'm actually going over some of this stuff when I wouldn't ordinarily, but you guys are supposed to be going back to basics. You're taking calculus. This is basically some of your basic physics you kind of need to know. It turns out a lot of electrical engineers, any electrical engineers in here? Okay, a lot of electrical engineers actually learn the voltage equivalent of temperature, because when you're looking at noise in an electrical circuit, you need to know how much thermal noise you can get. Okay? And if you really want to have really low thermal noise, like you're doing infrared detection or something, you often cool it to liquid nitrogen temperatures, right? To get rid of the thermal noise. Well, it turns out room temperature, which is about 300 Kelvin, many electrical engineers know is 25 millivolts if you go through this formula and put in Boltzmann's constant and the Coulombic charge. That's what I always remember. So it turns out, if this is 1/40th of a volt at 300 Kelvin, 1 electron volt is equal to about 12,000 Kelvin. So I can start breaking primary bonds if I have 12,000 degrees. Well, we know we break primary bonds at 12,000 degrees. There's very few things that remain solids or liquids at 12,000 degrees. They break the primary bonds and become gases, okay? You don't have to get 100% of the bonds broken to have something break from being a solid. You only have to have about 10% of the bonds break. So at much lower temperatures than 12,000 degrees. But I just proved to you on first principles that I can break primary bonds, nearly 100% of them, if I have 12,000 degrees of temperature. I just proved that most things will melt less than 12,000 degrees. Okay? That may not be that useful, but we can actually measure melting temperatures. But nonetheless, arcs will be a sufficient temperature. They can actually break bonds, and we know they do break bonds. Carbon dioxide in arcs breaks down to carbon monoxide and oxygen. Hydrogen breaks down into diatomic hydrogen. Anyway, lasers and electron beam. Well, an electron beam has a voltage on the order of, let's say, 100,000 volts. Okay? If you take that 100,000 volts and you take the same ratio, and you figure out 100,000 volts, what temperature in Kelvin is, you're going to get some sort of 100 million degrees. So an electron beam has an effective temperature of 100 million degrees. How useful is that? It's next to worthless to even say it, because that electron, when it hits an atom, doesn't transfer very much energy. Does anyone remember from probably your college physics, if you have two objects bouncing against each other, what the maximum energy transfer is between the two objects? You have to conserve energy and momentum. So if I have a billiard ball sitting here and another object comes and hits it, it turns out the maximum energy transfer is if the two things have exactly equal mass. So two billiard balls hitting together with no spin on the billiard ball, okay, you'll transfer 50% of the energy to the second billiard ball that was stopped. And what you do is you write down 1/2 mv squared of the incoming one is equal to 1/2 mv squared 1 plus 1/2 mv squared 2, because you have two objects going away, and V2 was 0 because it was stationary, but V1 was whatever it was coming in at. And then you have conservation of momentum, which is mv1 has to equal mv1 prime plus mv2 prime, and you solve two equations for two unknowns. And you end up finding that a 50-50, when the masses are equal, is when you get the maximum energy transfer. Okay, you solve that with your calculus. But in any case, an electron coming in with 100 million degrees Kelvin is not going to heat up that molecule it hits to 100 million degrees, because it's very low energy efficiency of collision. Okay, so you don't get 100 million degrees. If we could get 100 million degrees, we could do fusion, right?
But doesn't it shrink the heat affected zone when you're, if it doesn't transfer out?
No, because that electron bounces around and hits more and more atoms, and eventually gives up its energy, but not all to one atom. And it actually has a depth of penetration. When you get to electron beam welding later in this course, we'll talk about what the size of the heat affected zone is and how it gets controlled. And most of the stuff you read in welding will say when you go to very high heat intensity processes like laser electron beam, you can shrink your heat affected zone down to 0. It's wrong. Okay? It turns out you have to go back to the heat flow and realize that if you melt a little band of material, that band of material has a certain heat content to it, and as it loses heat, after the metal has been melted, the heat affected zone grows on cooling. And in fact, I'll give you in advance of what you'll hear later. If I plot temperature versus time for a weld, as the heat source comes in, everything's cold, and as it passes through some maximum, and then you have a cooling period after the heat source is passed. Okay, so if I'm sitting in one spot on a plate, and I'm sitting in this spot right here, and my heat source comes along, whether it's electric arc or whether it's electron beam or laser, and it's traveling along. If I'm sitting at that spot will first heat up to its maximum, and then when the thing is passed, the heat source is passed, it will cool down. It turns out for electroslag welds and arcs and other things, I form my heat affected zone on this heating part of the cycle. For lasers and electron beams, where I'm traveling much faster, I actually form the heat affected zone on the cooling part of the cycle. And so it turns out the width of the melted metal that I create ends up controlling the width of the heat affected zone, not the speed at which I heated it up. Okay? Because for very fast processes, it's the cooling time, not the heating time, that's important. Okay? Which is an error. You go read the welding handbook, it still tell you the things that are wrong. I once gave a talk on the errors in the welding handbook to the American Welding Society. A lot of people in the audience didn't appreciate it because they helped write it. But anyway, there are errors in the handbooks. Okay, so you can use temperature, and we use the full spectrum of temperatures that make any sense to try to clean off the surfaces and stuff. You also can use chemical potential. Well, cold welding, there's almost no difference in chemical potential. The fusion bonding, there is actually a difference in, you're getting rid of surface, and there's a small difference on the order of 10 to 100 joules per mole. Soldering and brazing have slightly larger ones. Thermite welding which is something the Navy also knows about. You might know why the Navy knows about thermite welding. Because when these rusty hulls in contact with the aluminum get hit by an explosive charge, or a gallon of gasoline or aviation fuel from the Belknap, or from the aircraft from the Belknap hit the carrier. Anybody know the Belknap disaster? Or is it too old? It probably occurred back in the 80s. A lot of you were still in elementary school and stuff. But they were having maneuvers, and the destroyer Belknap, or maybe it's a frigate, actually collided with the carrier. And I'm sure someone lost their command over that one. But when it did, I think it hit somewhere near one of the elevators. And anyway, some jet fuel fell on top of the Belknap, and it got ignited. And supposedly it wiped out the Belknap, because what happened is the hot jet fuel, that fire, helped melt some aluminum. The molten aluminum hit the iron oxide, the rust. Anybody ever seen rust on a ship? Okay.
No.
And molten aluminum hit the rust, and when molten aluminum sees rust, the aluminum has a higher affinity for oxygen than the steel does, or the rust does, and so it decomposes the iron oxide. And you will get temperatures of 4,000 degrees, okay, and 4,000 degrees centigrade, okay, and you can actually make wonderful welds. You can burn up entire superstructures, okay, and the joke at the time was a gallon of aviation fuel would wipe out any ship in the fleet. There is a debate, so far as I can tell, over whether the Exocet missile that hit the cruiser Sheffield in the Falklands War wiped out the Sheffield because of thermite reaction, because the Exocet missile actually set off set superstructure ablaze. Now, I said that once, and then some guy said, oh no, people found that's not true. I was told by the guys at David Taylor that was what had happened, okay? And one of the things they did in the early 80s after the Falklands War, or early to mid 80s, that's when they developed the waffle membrane construction for the superstructures, to get rid of the aluminum superstructures. You needed lightweight, but you know, they use this kind of corrugated steel now for your superstructure. Well, the reason they did that was because of the Sheffield and the Falklands War. You can go online, and there is a debate online as to whether that's what happened to the Sheffield or not, okay? So I don't know if it's what happened, but it certainly was the driving force, or at least it was what the guys at David Taylor were telling me and telling Congress in the open about why they wanted to go to waffle membrane construction of steel superstructures as opposed to aluminum superstructures.
I don't know if those super ships, but does the superstructure engines we build today, are they aluminum, or are they this waffle steel membrane?
So far as I know, most of them are the waffle stuff, although the Navy's going more and more, and isn't some of the littoral ships, the LD, what's LCX? LCS? It's supposed to be composite and aluminum mostly, because they want lightweight. Of course, the price is going, it's already over budget, and they haven't laid the keel, right?
So the explosive process we were talking about, joining the similar metals from superstructure with hull, that was an old process we used to use before we got this incident?
Well, certainly before the mid-80s. The ships before the mid-80s. In the 1970s, they would explosively weld the aluminum to steel, cut it up into little strips, and then they would weld regular aluminum to aluminum and steel to steel, because the explosive bond gave you the transition joint. So older ships have that. You still have some older ships built before 1985. Newer ships, the last I heard, they were still doing the waffle membrane construction. I've been to Bath, and I've seen DDX, but they don't let me up on the actual thing. And the only parts I saw in the other parts were all steel hull components. So I didn't get to the super. I didn't ask them. I assume that DDX is DDX, or is it frigates in Bath? Whatever it is, they've been. Not DDX, it's frigates. DDGs, I think, are the old waffle construction, because DDTs were designed, what, like 1990 or so, in that time frame. So I think DDGs are still the waffle, steel waffle. It's just basically big, thick, corrugated paper board made out of steel. It's just, it's just sheet metal that's got a corrugated shape. What they're planning for DDX and LCS, I'm not sure. Okay. for the superstructure. I think LCS is supposed to be composite and aluminum, and that's one of the reasons the price is going. I'm sure that's one of the reasons the price is going the way it is. So we use, this is kind of a way to look at all the welding processes. We use every way we can to get rid of surface contamination. Okay, there's a certain Gibbs free energy of those chemical bonds. We have to break off that surface contamination by one way or the other. And one of the ways we do it is cold welding. We just use pressure, lots of pressure. Now, I say lots of pressure. This can be anywhere from 10,000 to 100,000 psi. And I mentioned yesterday about thermocompression bonds on semiconductor chips. And we can pass that around. That's a picture of a thermocompression bond. Actually, that whole book is on thermocompression bonding. I estimated once we make about 50 trillion of these welds a year. 5 times 10 to the 13th of these welds a year for semiconductors. And in fact, you have this in your handout of chip-to-package interconnection. And this is a picture of a thermocompression bond. It's on page 394 of your handout. But basically, I have a little sewing. It looks like a $50,000 sewing machine, because that's basically what it is. And you thread, rather than a cloth thread or a nylon thread, you have a little head here that you feed a wire through, typically gold wire, about 1/1000th of an inch in diameter, or sometimes, anyway, well, 1/1000th of an inch is 25 microns. Standard size right now is 20 to 25 microns, so 8/10,000ths of an inch or so. And you just slam it into the surface, and they do these things about 7 to 10 times a second. So when this thing's going, it's going faster than the sewing machine. And so just the mechanical inertia of this head has to be lightweight but strong, because you're going to take that gold wire and just smash it onto the surface of the chip, which may have aluminum, and you'll get a gold aluminum joint. And then you take that wire and you take it out to another pad, and you actually can cut it off. Or sometimes they'll have a little hydrogen arc here, and it will melt the surface, so you end up with a little surface tension will form a little ball on the end as you melt it, and then you smash the melted thing into the surface, and you get a similar type of bond. So that's the little wire bond that we use for making semiconductor attachments. It's basically a cold weld. And one of the things we've learned about cold welds is you have to have some interfacial sliding to get good cold welds. If you just push things together as hard as you can, you won't get a good bond. Okay? And we'll go over tomorrow why that is, why you don't get such a good bond when you just push them together. But if you slide them together, you will get a good bond. And I'll pass these around tomorrow, because there's not enough time to all of you look at them today. But there are various ways we do this. One of the oldest is to do friction welding. And this is just 2 steel bars, 1 inch in diameter. Grab one of them in a chuck, like a lathe, hold it stationary. The other one you'll spin at high speed, and you'll push them together, and the friction will generate heat. There's actually a heat effect zone around this, and I will upset the surface. I mean, this thing will start to glow red. On the website, there's actually some videos, and you actually see friction welding being done. You push this together, within a fraction of a second, this thing starts to glow red, because you have so much energy stored. And you may have a big flywheel on one stationary and the other one's spinning. You got enough energy in a great big flywheel that all that energy gets absorbed by the friction here, and you ram them together and forge them together. It's not really a cold weld, but it is a pressure weld that starts out cold, adds a little heat to it, forges it together, and you extrude out the surface contamination. Now, on your drive shaft of your automobile, you have a universal joint, which basically is a little yoke that is bonded to in the old days it was a steel tube. They're actually going to graphite fiber tubes, because in a car the drive shaft goes pretty fast, and lightweight is important. The faster something goes, But in the old days, they actually used to take the cast steel yoke, hold it in the chuck, and then take the tube that they want to weld it to, and they would make a friction weld. Friction welding is very fast, 2 or 3 seconds, maybe 5-second cycle time. If you got everything set up right, you can make very good welds, very reproducible welds very quickly. If you got things set up wrong, you can make junk very quickly. Okay, so you have to get it set up right. Now, in jet turbines, people actually will take a $30,000 or $40,000 titanium disc, and they want to weld it to another titanium disc. So you got two $30,000 parts, and you will friction weld those together. Okay, and if you don't do it right, you end up with $60,000 worth of scrap. If you do it properly, you end up with a $100,000 product. You probably just made $40,000 by welding them together properly. So they do it on very high tech. They do it on somewhat low tech things. Another thing that's fairly popular now, these people like to talk about it, is friction stir welding. One of the reasons for spending all this time on all these different things is the American Welding Society lists 199 different welding and cutting processes. I once went through those for a talk I had to give at a welding conference and pointed out the first 75% of those were developed in the first 50 years of the last century. And then the next 24.8% were developed in the next 25 years, between 1950 and 1975. And I could only think of one process, one new welding process that had come to fruition from 1975 to 2000 when I gave the talk. Okay? So 75, when welding's a relatively new field, it really didn't start blossoming until the early 1900s. It wasn't, arc welding didn't start until Edison and Westinghouse came and gave us a ready source of electricity. That was in the 1880s. Humphrey Davy had invented the electric arc, or discovered it, in 1805. But no one had a source of electricity in the size and quantity they needed until Edison and Westinghouse. They started arc welding in the 1880s. It was really still sort of a curiosity by World War I. By World War II, they actually started using it for some major things. The first critical use of all welded structure was the Big Edge pipeline. I think I mentioned that in about 1930, which brought gas from Louisiana. The friction stir weld, this is a NASA friction stir weld. They basically take a mandrel and they fixture the plate very, very well. And they come in and they spin the mandrel around and just move it along the plate and make a weld with very little distortion. If you compare that to an arc weld, those plates would be 15 degrees for a typical fusion arc weld. It's a solid state process. No?
Does the surface weld though? I mean,
no, it goes all the way through. The mandrel actually pushes down beneath the surface. And they have done up to ½ inch thick. Boeing is doing friction stir welding right now. And it's kind of let you go, but I'll show you these tomorrow. This is an ultrasonic weld, which is a form of cold welding where you have to get some vibration. And then plastics is another example. This is a piece of gas pipe for laying gas pipelines in the street. So we can talk about that tomorrow. But we'll pass this around so everybody can see it tomorrow.